In engineering, the forces inside a material aren't always aligned with our standard X and Y axes. To understand how a material will truly behave, we need a way to see how these internal forces, or stresses, change as we look at the material from different angles. This is called stress transformation. Let's imagine we could look inside a loaded structure, say a steel beam. If we zoom into any single point, we'll find it's experiencing a certain state of stress. To describe this state of stress, we can imagine isolating a tiny square element of material around that point, aligned with our standard X and Y coordinate system. First, we have normal stresses, which pull the element apart or push it together. We label these sigma X and sigma Y. By convention, tension is positive. We also have shear stresses, which try to deform the element by sliding its faces past each other. We call this tau xy. For the element to be in equilibrium, the shear stresses on all faces must be equal and balanced. This setup gives us the stresses on planes aligned with the X and Y axes, but the maximum stress in the material might be acting on a completely different, inclined plane. How do we find the stresses on such a plane? To answer this, we need to find a relationship between the known stresses in the XY system and the unknown stresses, let's call them sigma x prime and tau x prime y prime, in a new coordinate system rotated by an angle theta. The key to deriving these relationships is to use the most fundamental principle in mechanics, equilibrium. We can imagine slicing our original element to create a small wedge. If the whole element is not moving, then this little wedge must also not be moving. Let's say the area of the inclined face is delta A. Using simple trigonometry, the area of the vertical face is delta A times cosine theta, and the area of the horizontal face is delta A times sine theta. Now, we can turn these stresses into actual forces by multiplying each stress by the area over which it acts. These are the known forces acting on our wedge from the rest of the material. These known forces must be balanced by the forces acting on the inclined face. These are the forces we are trying to find, which correspond to the new stresses, sigma x prime and tau x prime y prime. The principle of equilibrium says that the sum of all forces in any direction must be zero. Let's start by summing all the force components that act along the new x prime axis. We have the main unknown force, sigma x prime delta A, and then we subtract the components of all the other forces that are projected onto the x prime axis. The entire sum must equal 0. This looks complicated, but notice that delta A, the area, is in every single term. This means it cancels out, which makes sense. The stress shouldn't depend on the size of the element we choose. After rearranging, we get our first transformation equation. This equation is correct, but we can make it more elegant and useful by applying a few trigonometric identities. These double angle identities will help us combine terms. After substituting these identities and doing a bit of algebra, we arrive at the final standard form of the transformation equation for normal stress. This beautiful equation gives us the normal stress on any plane, just based on the original stresses and twice the angle of rotation. Great, that's half the problem. Now we need to find the shear stress, tau x prime y. We do the exact same thing, but this time we sum the forces in the y prime direction. Following the same logic of projecting each force, summing them to 0, and canceling the area term, we arrive at this expression for the new shear stress. And once again, we can simplify this using our double angle identities to get the final clean transformation equation for shear stress. And there we have it. These two equations are the heart of stress transformation. Starting with any state of plane stress, we can plug in any angle theta and immediately find the normal and shear stresses acting on that new plane. This is fundamental for finding the most critical stresses in any mechanical design.